Good morning. You guys have about 5 minutes to work through these problems, and then we will get started for the day. All right, so that's loud. I'm gonna start going through these problems, a little bit of a review from chapter 9, which we covered on Friday. So this first reaction is a bromination. We've got Br2 and a triple bond. We're doing it in excess. I'm gonna kind of go through it stepwise. If we were to do the single bromination, we would add Br across this triple bond in anti-position. So we'd originally get something like this, and then upon our second bromination, because we are in excess, we're going to end up with 4 bromines. Giving us this product here. Next problem is H2 and Lin-Lars. So that's essentially our normal reduction, except we're using our poisoned catalyst, which will stop us after the first reduction. So H2 adds Sin to a double or triple bond. So it's going to end up giving us our cis product from this reaction, like so. This one down here, so I should have water in here also. We are adding an alcohol across our triple bond here. So we'll initially get something that looks like this, and then through an acid catalyzed polymerization, we can grab an H+. Lose that proton and get our ketone product. So this is a Markovnikov type addition. We have a primary and a secondary center. And we end up adding to that secondary center, making it a normal Markovnikov type addition. This one over here, we are going to do, again, Markovnikov type addition. So we have a primary center and a secondary center. Our Br is going to add to that secondary center. In the first addition, we would get something that looks like this. And then upon adding a second equivalent of HBr, we can dibrominate. Our 9-BBN reaction, or in peroxide, we're going to be adding anti-Markovnikov. We're originally going to get this compound here. Someone in the chat asking people to mute themselves. And then through base catalyzed. So we're in NaOH. This can pull up the proton. Pick up a proton, and we'll make an aldehyde. Our last one is our radical reduction of this triple bond here, which is going to end up giving us the opposite of what H2 and Lin-Lars does. We give the trans double bond. Any questions on these ones? Okay, so I'm briefly going to talk about some reactions from chapter 9, and then we're going to do chapter 10 today. Chapter 10 is pretty straightforward. I'm only going to cover 4 of the reactions from the chapter, 2 of which I believe you got. One you saw last semester, another one is from chapter 8. We just don't really give a mechanism for it. But, so taking a look at ozonolysis. So this is something you guys learned back in chapter 8, that if you take a double bond and you throw in O3 DMS, essentially you can break this double bond, and it's a much more convoluted mechanism than this, down the center, and you'll generate this here. So I kind of dot these out. This green portion would be your left side of the molecule. This red portion would be your right side of the molecule. You've essentially just kind of stretched this bond and shoved 2 oxygens in between them. For a triple bond, it's basically the exact same reaction. So we take O3 and H2O. We're going to break our triple bond in half. Up here, we were generating 2 bonds to oxygen when we did this. For a triple bond, you're going to generate 3 bonds to oxygen, which is going to look like a carboxylic acid. So, doing kind of the same thing here. This green portion, which was 2 carbons, one of them being part of the triple bond, is now this part here. Someone asked, is O2 always used for alkynes as opposed to DMS for alkenes? Yeah, it's just 2 different reagents for that second step of the mechanism, which I'm not going to cover because it's fairly complicated. So you just need to memorize that for a double bond you use DMS, and for a triple bond you use H2O. For the other half of the molecule, these 3 carbons here, the end one being part of the triple bond, is going to end up being these 3 carbons here. If you do okay, so I'm going to move on to a much more important reaction, which is alkylation using a triple bond. So if I take a triple bond that is terminal, so I have an H at this position here, and I throw in NH3, or sorry, NH2, I can pull off this proton. Making a negatively charged carbon. And from this point, if I throw in some sort of alkyl halide, I can do an SN2 on this center, kick out this iodine, and add that carbon unit to my alkene. So this is really useful because up to this point, this is our only reaction that makes a carbon-carbon bond. which is something that's going to be really useful if you want to do synthesis, things like that, where we're going to need to be able to build molecules. So taking another example of this, and then we'll talk about some more complicated examples of it. So I'll walk through some synthesis for this. Na, NH2, this alkyl halide here. So our first step, going to pull off this proton, generate a negative charge. From here, we're doing an SN2 reaction. And we can add this large carbon group here. You can actually do this twice if you have this ethyne here. So if I take this compound and I throw in NaNH2, I can essentially do this reaction twice and add two different alkyl groups to it. So first step, pull off this proton, give us negatively charged triple bond. This could do a nucleophilic attack. We would generate this alkyne, and then we can kind of rinse and repeat. NaNH2. If we now throw in a different nucleophile, or electrophile, sorry, like this here, when we generate our negative charge, we can do an attack and give us this compound. So like I said, this is very useful when we start getting into synthesis, which I believe is probably going to be Friday because our schedule is a little pushed back from that snow day. I'm going to give kind of a brief reason why, though, right now, just to kind of get you guys to be thinking about that. So if I want to do a synthesis, I'm starting here, and I need to get to this as my end product. So this is going to be a quick one. This is going to be a two-step synthesis. Looking at my starting material and my product, this is most likely going to map onto this here, which means that we need to add more carbons because our starting material has less carbons than our final product here. We also need to reduce a triple bond down to a double bond. So again, I'll talk about this a little bit more when we get into synthetic strategies. There's really two different reactions that you need to do here. You need to do a reduction and you need to do an alkylation. And I'm going to draw them both out and talk about why the order of them matters. So if I take this triple bond, I throw in Na0, NaH3, or H2 and Lindlar's, I can make this. This is going to be a dead end we can't do an alkylation. We only know how to do alkylations from triple bonds, so getting to a double bond is going to kind of stall us out, versus if we were to do NaNH2, this is 3 carbons, 1, 2, 3. Our alkylation first. And then from this point, doing our same reduction. We can actually get to this final product. So again, this is kind of a preview of what we're going to talk about on Friday. We're going to actually break down synthesis a little bit more. But just know that like when we start doing these, your order is going to be very important, because if you get to a point and you do reactions a certain way, you might end up at these kind of dead end points where you don't have a reaction to go to the next step. Okay, I'm going to move on to radicals. So like I said, we're going to cover 3 reactions from the radical chapter. I think one of them you guys did in 251. The other one is just HBr and peroxide, which you guys are pretty familiar with. I don't know if you guys covered a mechanism for it. But a radical is essentially a carbon that has, as opposed to a lone pair or a positive charge, we think of like a lone pair as being negatively charged versus a positive charge where you have no electrons. A radical is kind of the in-between. You have one single electron. It is neutral. It's also really reactive. Its stability is going to be the same as what you'd expect for a negative or a positive. Your least stable radical is going to be something like this, where you have it on a primary center. And as we start going up in stability, so if we have a secondary center, that's more stable. A tertiary center, more stable than that. And then when we start getting into things with resonance, that's going to be even more stable. So same principles you guys learned for negative charges apply to radicals. Same with resonance. You'll have the same kind of resonance you did with a negative charge with a radical. When we move radicals, we use a half arrow. So let's see. For this negatively charged species here, if I want to move this double bond over, I'm going to use a full arrow to show that these 2 electrons are shifting. And then same thing over here, a full arrow shows that the 2 electrons from the double bond are moving over to the right here. For doing resonance on a radical species, we're going to use half arrows, and that symbolizes moving 1 electron instead. So a half arrow would look like this. So it looks like this. We only have half an arrowhead versus this, we're using a full one. And that symbolizes that we're moving 1 electron instead of 2. So we move this one electron over. We need to get a second electron. So we're going to steal one from this double bond here. That makes 2 electrons. To make the double bond there, our other electron that was on our double bond is going to get kicked to the end. And that'll give us our other resonance pair. Resonance follows the same form as it would if this was a positive or a negative. We just slightly change. Whoa, did we lose the lights? Interesting. Okay. Follows the same form as which were positive and negative. You're just moving these single electrons instead. So first reaction I'm going to talk about is a simple bromination reaction. If I take an alkane and throw in Br2 and light, this is light. This is going to brominate at its most stable position it can. So right now we have 3 primaries and a tertiary position. Tertiary is going to be the most stable position, so we're going to end up adding Br here. This is really useful because you need some sort of group to do chemistry. Currently, this alkane has nothing on it, so being able to brominate it will allow us to kind of do more reactions, and it's a really useful synthetic tool. So how this works is it's going to be a 3-step process. Radical reactions have very different mechanisms than anything else in this class. The first step is called initiation. And essentially what's happening is you're starting with 0 radicals. And you're going to create something with 2 radicals. Or you're going to generate 2 radicals. So if we have Br2, and we hit this with light, I'm going to draw this squiggly little line here. This is going to split this bond here into 2 electrons. So this will give us a Br radical plus a second Br radical here. Our second step is called propagation. And in propagation, you're going to have 1 radical on your reactant side, and you're going to end up with 1 radical on your product side. So if we take the radical that we just formed over here, this Br, and we add it in with our alkane here, it is going to do what's called a hydrogen extraction, which is very similar to grabbing a proton. So 1 electron from this most stable center is going to react with our Br. We're going to form a bond between this hydrogen and this bromine. It's breaking this bond here, kicking this electron down to our more stable center. We're going to form HBr plus this carbon radical. So we started with 1 radical, which was this Br radical, and we've now generated this carbon radical. Propagation generally has 2 steps. The second step, you're going to make your product as well as remake this bromine radical so that this process can continue. So if we take our carbon radical plus an equivalent of the BR we started with, BR2 we started with, we can have our radical plus one of the 2 electrons from this bromine come together to make a bond. We will break this bond to our bromine. Generate one equivalent of our final product plus BR radical here. And this is really important because we need to generate this BR radical so that this can go up, enter back into our system, and we can redo our cycle. So propagation is like a cyclic system. You want it to keep happening over and over again. So if you don't end up making your starting material, you can't do that. The last step is termination. So 1, 2. And termination is we're going to be where you take 2 radicals and you generate something with 0 radicals. So if we take, there's, for this case, 3 different options. BR radical plus another BR radical. We can make BR2. And then this can just get fed back into our system somewhere, maybe down here. We can have our BR radical and our carbon radical come together. This would give us our major product. And then the other option is to have the carbon radical react with itself. And this is going to give this weird looking byproduct. Okay, so brominations are pretty straightforward. If I have something like BR2 in light here, it is realistically going to just add to this tertiary center. It's the most stable center. We have a secondary, we have 3 primaries. This is probably going to be our major product. And mathematically, there is a selectivity factor for these. So brominations selectivity looks something like, for a primary versus secondary versus tertiary, you have a 1 to 80 to 1600 ratio. So this bromination on a tertiary center is drastically more likely to happen than it would be on a secondary center, than it would be on a primary center. And I'll kind of explain this selectivity in a second when I talk about chlorinations. So when you look at these brominations, essentially, if you have a tertiary center or whatever your most stable center is, it's dramatically more likely to add to it than it would the next most stable center versus the least most stable center. Chlorinations are not as picky. So we can do the exact same reaction with Cl2 in light. It'll follow the exact same mechanism as before. But we are going to end up with some ratio of these four products here. So we have a tertiary center, secondary center, primary center, and then these two primary centers in the end are the same. Get it symmetrical. The selectivity for chlorine is 1 to 4 to 5, which is not very dramatic. So I'm going to go over exactly what that means and how you would actually calculate that. So I'm just going to kind of redraw this on another page. We've got this molecule here. We're adding in Cl2 and light. We've got selectivity factors. For different stability, so 1 to 4 to 5 here. So how you're going to calculate these is you're going to multiply the number of H's times its selectivity for each position and then divided by the total for every position. So taking this first one as an example, I am going to start with just this H here. So this is a tertiary carbon, which means its selectivity is 5. There is 1 hydrogen on it. So our total selectivity factor for this is going to be 5 here. Moving on to this secondary position, we have 2 H's on it. It is a secondary position, which means its selectivity is going to be 4. So this was 5 times 1 equals 5. There are 2 different protons you could possibly pull off of here. So this would be a selectivity of 4 because it's secondary times the 2 protons. Gives us a likelihood, in this case, of 8. Moving on to this back position here. We've got 3 protons down here. So 1 is primary times 3 equals 3. And then our last option is these 2 symmetrical CH3s at the end. So there are 6 protons between those positions. It's primary, so 1 times 6 equals 6 here. So to figure out what percentage each of these is going to be, we need to add up the total. So 5 plus 8 is 13, plus 3 is 16, plus 6 is 22. So our ratio is going to be out of 22. So this is 5 out of 22, 8 out of 22, 3 out of 22, and 6 out of 22. And that would give us our percent yield of each of these, theoretically, if we're at 100%. So from this, we can determine that this secondary position is actually going to be our major product because it has the highest selectivity. So chlorinations are a bit of a mess. You get a lot of different products from these, and if you think back to our mechanism over here, when we're doing this termination step, you're going to have 4 different possibilities here, so these tend to be a bit of a mess in general. But that's chlorinations and chlorination selectivity. I'm going to go over HBr and peroxide, and we'll see if we have time for NBS or not. So HBr and peroxide is a reaction that you guys have seen for a really long time now. So this gives us this product. You guys have probably already know that. You may not know why it gives us that product, but we're going to talk about that right now. So our mechanism for this is going to be pretty similar. We have, for whatever reason, there's 2 different initiation steps. That's how they decided to group it for this. So our initiation, is going to involve our peroxide being split in half. And this is going to give us 2 radicals of OH dot. From here, this can react with HBr and we are going to get water plus a Br radical here. In our propagation step, we're going to take this Br radical and we're going to react it with our alkene here. And when we do this, so we're going to form a bond between the Br and our alkene, and then the other electron is going to get kicked to the more stable position, which is going to be this secondary center here. And that's going to give us this radical. From this point, this radical can react with another equivalent of HBr. So we'll pick up a hydrogen. Our other electron from this double or the single bond here can go to our Br. We'll get our normal product plus Br radical. For termination, there is a lot of options. I'm only going to go through a simple one. A lot of the times for these mechanisms, you really only need to draw one termination product. At least that's what the book is doing, so I'm going to do the same. So if I just draw Br radical plus Br radical coming together to give us Br2, that would be acceptable for one of these kind of mechanism questions. 5 minutes. So I'm going to talk about NBS. And we'll kind of see how far I get into it. I might cover it a little bit again at the end of, or the beginning of Wednesday's lecture. So NBS is N-bromosuccinimide. And essentially what it's going to do is we're going to end up adding a bromine next to a double bond as opposed to HBr and peroxide, where we replace the double bond with a bond to bromine. So this is a little bit larger. It looks something like this here. I'm not going to go through the full mechanism right now. I'm just going to kind of talk about if I have something that's a little bit more complicated. So this compound, for example, at some point in time, in order to make this, we are going to have to pull off. This is kind of different than anti-Markovnikov. Someone asked in the chat if this was be considered it. This is kind of its own thing. So we're going to be looking at the protons that are next to our double bond, or the hydrogens that are next to it. So we have an H here and an H here. We can generate, oops, if I'm remembering. Most likely we're going to generate this radical, as this is our more stable hydrogen to pull off. From this point, we have two different possibilities. And I haven't really talked that much about double bonds. Oh, man, I keep drawing sigma rings. We have these two possible radical species, and both of these can go to make a product. So these start getting complicated pretty quickly. I'm just going to redraw this once on another page. And then we'll actually go through a full mechanism for these on Wednesday. So if I was to take this compound here, throw in NBS, it's going to brominate at the position that is next to our double bond, the more stable one. So kind of review, we had a tertiary one and a secondary one. It's going to most likely brominate at our tertiary one, but we're also going to make a radical that has resonance at some point. And we can also get this product. So we're going to go over these a lot more in detail on Wednesday. That's all I have for you guys right now. I will see you guys then.